Thus far, we've been looking at tests of statistical significance that concern a single variable. For example, we've looked at techniques for determining whether a sample mean is different from a population mean, or whether the means from two or more different samples differ statistically. We now move on to look at the relationship between variables. The underlying question now becomes, if I know something about a particular person or group, does that improve my chances of predicting something else about them? For example, if I know that you're married, can I predict your level of life satisfaction? Or if I know your political party affiliation, does that improve my ability to predict whether or not you believe climate change is caused by human activity? These are the kinds of questions we can answer with a multivariate analysis. Put differently, we're examining with these techniques whether two or more variables are independent of one another. Do they vary together? In other words, as one goes up, the other goes down, or as one goes up, the other one also goes up, or do they vary independently of one another? The starting point for this simple bivariate analysis is known as contingency table analysis, and we'll create bivariate tables, contingency tables, crosstab tables. These are all synonyms for the same thing. Here's an example. This table shows the relationship between a survey respondent's race and his or her political party affiliation. By convention, we set tables up so that the independent variable is in the column position and the dependent variable is in the row position. Each of the cells in this table shows the number of respondents in each of the categories. 96 were white and identified with the Democratic Party. 54 were African American and identified with the Democratic Party, etc. The values shown here in green are called the cell counts, or observed values. If we read across the table, we can see that 150 Democrats, 150 Republicans, and 100 independents responded to the survey. Reading down the columns, we can see that there were a total of 300 whites and 100 African Americans. The row and column totals are called, respectively, the row marginals and the column marginals. A total of 400 people completed the survey. Let's now return to the question we started with. Does knowing a person's race help predict their political party affiliation? Well, as the table shows, there are more whites who are Democrats than there are African Americans, 96 as compared to 54. But of course, there are more white respondents, 300 overall, as compared to 100 African Americans. So clearly, simply looking at these cell counts doesn't make that much sense. We need to look at the percentage values. In this table, we've computed the percentages of whites and African Americans in each political group. Notice that we've computed these percentages for each of the independent variables. This is critical. In order to understand whether changes in an independent variable affect a dependent variable, we have to compute them this way. The easiest way to remember to do this is to place the independent variable in the column position and then percentage down the columns. If we percentage the table as shown in this slide, that is, we percentage across the rows, there really isn't that much of interest we can say. So what if 64% of the Democrats in our sample were white? All we're really doing here then is making a statement which describes the population in general. Since there are more whites in the United States than African Americans, you'd expect that there'd be more whites in each political party. That's not very interesting. We could also have percentaged the table to show the individual percentages in each cell. But again, this isn't of much value. All it tells us here is that 24% of the people in our survey were white and Democratic, and that 14% were African American and Democratic, etc. Again, there's nothing interesting here because we're not saying anything about the relationships between variables. For that, let's go back to our original table where we percentaged down the columns. Okay, so again, you can see that knowing your race helps predict your political party affiliation. For example, if I know that you're African American, I know there's a much better chance that you'll be Democratic. Why? Because 54% of African Americans are Democrats. Similarly, if I know that you're white, you're nearly twice as likely to be a Republican. Again, why? Because 41% of all whites are Republican. A larger percentage than for any other political party. You should be able to see here that if you're white, you're more likely to be Republican than anything else. Now the question becomes, are these predictions based on differences which are statistically significant? How do we determine statistical significance with these kinds of data? Well, the answer is to compare the observed cell counts with the cell counts that we would expect if there was no statistically significant relationship. In order to do that, we need to figure out how to compute the expected cell counts. So here again are our observed cell counts. The first thing you'll notice is that 3/4 of the respondents are white and 1/4 are African American. If 3/4 of all our respondents are white, then we would expect, if there's no relationship between race and political party, that 3/4 of our Democrats would be white, and that 3/4 of our Republicans would be white, and that 3/4 of our independents would be white, plus or minus some random variation. To calculate the expected counts in each cell, we simply multiply the number of Democrats, in this case there are 150 Democrats, by 3/4. This gives us an expected cell count of 112.5. 1/4 of the total sample is African American. So by the same logic, we would expect to find that 1/4 of all Democrats would be African American if there was no relationship between race and political party affiliation. So again, if there are 150 Democrats, we would expect that 37.5 of our respondents would be both African American and Democrat. To figure the expected values for each cell, you multiply the row marginal value for that cell by the column marginal value for that cell and divide by the total N for the sample. In this table here shows the results for all 6 cells. You'll note that in this case, because there are 150 Democrats and 150 Republicans, the expected cell values are the same for whites and the same for African Americans. This is purely by just a coincidence. The statistic that we're going to need to determine whether a relationship here is statistically significant is called chi-square. This is the symbol for chi-square. You definitely don't want to confuse this with x square, even though in this particular font that's what it looks like. But at any rate, chi-square is equal to the sum of each observed value minus its corresponding expected value squared, divided by that expected value. Just like the other tests that we've looked at throughout the course, the numerator holds the difference between the observed value and expected value, and the denominator holds the expected value. Unlike the other tests we've looked at, the denominator is not a standard error, but simply the expected value. Why? Well, a standard error doesn't really make sense when you're talking about a categorical variable. There's no standard deviation upon which to base a standard error. But the ratio functions the same way. The observed value is very different than the expected value, which is likely in a statistically significant relationship. Then the numerator goes up and the value of the fraction goes up. As usual, the higher the value of the test statistic, or the fraction, the more likely it is that we'll reject the null hypothesis. So as we've done in the past, the easiest way to solve these problems involves setting up a summation table. Here's the summation table for this problem. This column over here shows the observed values. They're just taken from the table. This column shows the expected values, which we calculated just as I described. And to compute the chi-square statistics, we simply sum the values in the rightmost column of the table as shown in the formula in the last slide. In this case, the value of chi-square is 15.52. Just like z and t, chi-square has a probability distribution, and we therefore need to look up a critical value for that distribution in a chi-square table. To do that, we first need to figure out the degrees of freedom that we're working with. For chi-square, the degrees of freedom are given by the number of rows in the table, -1, times the number of columns in the table, also -1. In this case, there are 3 rows and 2 columns, so we have 3 minus 1 times 2 minus 1, which equals 2. With that value computed and the value of chi-square known, we can turn to the table and look up our critical value. Here's a sample chi-square table. As you can see, we read the degrees of freedom down the rows and the alpha level across the columns. In this problem with 2 degrees of freedom, you can see that we have a critical value for chi-square of 5.9915. Based on our expected values, the ones we calculated, the value of chi-square in our problem is 15.52, so we can reject the null hypothesis and conclude that there is a statistically significant relationship between race and political party affiliation. That's pretty much it. Conceptually, chi-square operates in a way very similar to the other tests of significance that we've been working with. It answers the question, are the observed differences between the cell counts different from what we would expect to see if there was no relationship between the variables? It's worth pointing out that we can use chi-square for any number of columns and rows, though interpreting the results for a contingency table with many rows or columns becomes impractical. There are better techniques to use in those circumstances. Before we finish up, let's just note that in order to use chi-square, we need to be sure that the expected counts of the cells are equal to at least 5 cases. For tables with only 2 or 3 levels of each variable, this is usually not a problem. But if you start getting into tables with more than just 2 variables or multiple levels of each variable, then things start to get tricky. For these kinds of problems, there are better techniques to use, but they're a bit beyond the scope of this course. Okay, well, I hope you found this video useful.